Problem number 3 on quiz from Unit 1.2 starts out with a single infinite sheet of charge, and we're told that the surface charge density is equal to negative 3.54 times 10 to the negative 6th coulombs per square meter, or if you prefer, microcoulombs per square meter. There's a string that's attached to a small plastic bead that's suspended at an angle of 10 degrees. The first thing we have to solve for is what's the electric field at the location of this bead. Now we know if this really is an infinite sheet, in other words, if the dimensions of length and width far exceed this distance that we call d, then the electric field is uniform throughout all of this region, right? We'd have to get really far away before we notice the field lines actually start to become non-uniform. So we apply Gauss's law. We choose a Gaussian surface, something like this. The integral of EdA is Qn over epsilon naught. The amount of charge inside of that Gaussian surface is represented by that shaded area. Now I'll skip a couple of steps here. If you need to review how you can go through each step and find the solution, I encourage you to do so. But you probably remember that in this case the electric field is just sigma, the charge density, divided by 2 epsilon naught. This 2 has something to do with the fact that there's flux through that end and there's flux through this end. Okay, so we plug in the given values. 3.54 times 10 to the negative 6 coulombs per meter. You know the value for epsilon naught. So grab a calculator and double check me on this one. But the electric field should come out to be 2 times 10 to the 5th newtons per coulomb when applying this formula. Part B, we have to draw a free body diagram for the plastic bead. So there's clearly some tension pulling up and to the left due to the string. We can't ignore the fact that the bead has some mass, so its weight is calculated as mg. Now, this does not represent equilibrium. There's obviously another force acting. The reason why it's hanging at a 10-degree angle, there's an electrostatic force pushing in this direction. So we can just label that as F subscript E. It might be worth noting that that force is equal to nothing more than the charge of the bead multiplied by that electric field that we just solved for in part A. It would be a mistake to say that this force could be calculated as K Q1 Q2 over R squared. That's the type of formula we would use if we had 2 point charges. This is a point charge interacting with an infinite sheet, not a point charge interacting with another point charge. Part C, find the mass of the plastic bead. Solve for this value of m. So if I get rid of the tension vector and replace it with its components, then this is T times cosine theta. This is T sine theta. So we know that T sine theta has to equal QE if our free body diagram represents equilibrium, and T cosine theta equals mg. If we divide one equation by the other, tension cancels out, and we have tangent theta equals QE over mg. Or in other words, I'm sorry, we're not trying to solve for the mass. We're given the mass. We're trying to solve for the amount of charge. Okay, so Q is equal to mg tan theta divided by E. So if we use all the given values, we're told that the mass is 0.9 times 10 to the negative 3rd kilogram. We know what to plug in for G, right? The angle is 10 degrees. We just found E in part A. So plug in all the given values, and you should find that Q is equal to 7.78 times 10 to the negative 9th coulombs. Now this sheet of charge that has the given charge density of negative 3.54 microcoulombs per square meter still sits here, and then two more sheets are brought into the vicinity. This one has a charge density of positive 1.77 microcoulombs per square meter, as does the third. Now we notice that 1.77 is exactly half of 3.54. So if we were to picture a point over here and try to find the electric field, there's a component of that electric field that points to the right due to the negative charge distribution on this sheet. This sheet has a positive charge distribution, so that makes an electric field that points to the left. And I've drawn that vector exactly 1/2 the length of the first vector. Because notice, we're told that these are sheets of infinite dimension in terms of their length and their width. So it doesn't matter that this point is farther away from this sheet of charge than it is this sheet of charge, because this dimension I might call D doesn't factor in to the strength of the electric field. So if it's half the amount of charge, it's half the intensity of the field. In other words, if I call this something like E naught, then this is going to be 1/2 E naught. And of course, this sheet here also is going to produce a vector pointing to the left of 1/2 E naught. And so the net result of all this is that the electric field in region number 1 is equal to 0, and that's the answer to part D. So if you extend this logic, if you make a dot for region number 2, region number 3, and region number 4, and the question is to find where would the electric field be the greatest. Well, again, in region number 4, by the same logic we had in region number 1, the electric field here is also going to be equal to 0. So in region number 2, there's an electric field pointing to the left of E naught. There's also, to the left, an electric field of 1/2 E naught, and also to the left, another 1/2 E naught. So I hope you understand how I've chosen the directions of each of these vectors. Okay, so there's no cancellation. The net electric field would be 2 E naught. However, in region 3, we're going to have this vector to the left that I'll call E naught. There's a vector to the right of 1/2 E naught, and there's a vector to the left of 1/2 E naught. So yeah, clearly the greatest strength field is going to be in region number 2, and that was our answer to part E of this quiz.